April 2020 semester ICT 6900 Special Topics in ICT Advanced Machine Learning কোর্সে সবাইকে স্বাগত জানাচ্ছি। Today we'll cover lecture 4. The topics of the lecture is Logistic Regression and Regularization. So in the lecture 1, we discussed about classification problem. This is also supervised learning, and type of learning is classification. So let us first of all discuss some examples of classification problem. For example, you want to distinguish between spam email or not spam email. So the algorithm should be applied is classification algorithm. And in online transaction, you may want to determine whether a transaction is fraudulent. Yes or no. Either fraudulent or not fraudulent. Similarly, if you want to detect the tumor, whether it is malignant or benign, you can do with the classification problem. So normally we have the data between 0 and 1, yes or no. In all the examples that we have cited, either the data will be yes or no, output data will be yes or no. For example, in case of tumor, we group the data having 0 as a negative class, that is benign tumor. And for positive class, we denote it by 1, which is malignant tumor. So there are two options of the output, either it is 0 or 1. But in the later part of our class, we'll discuss about the output can be multi-class. It can be 0, it can be 1, it can be 2, or it can be 3. So for the time being, let us concentrate on the two-class problem, either positive or negative class. And if we understand this development, we can easily extend it to multi-class classification problem. Let us recollect our previous lecture where we discussed about the regression problem. And what we did in those problems, that we fitted a curve, either linear or nonlinear, through the given data. And from that curve, either a straight line or polynomial curve, we found out the unknown cases. That means the output for the unknown cases. So similarly, if you want to proceed with that kind of hypothesis, how it will be applicable for this kind of problem, classification problem. So let us say we have a data of tumors. Those data are for benign tumors and those data for malignant tumors. And we want to distinguish these two kind of data through an hypothesis. Let us say we fit a curve of hx equal to theta t x, where theta is a vector and you have to take transpose and multiply it with another vector of x. X is a feature vector and theta is the parameter vector. So let us fit this equation through this data. And let us say this is the line. And if you get the line, one algorithm you can set that in the 50% of this level between 1 and 0, that means when hypothesis value or the output value is 0.5, then we can say this side will be the malignant side and this side will be the benign side. That means the tumors where the h theta is more than 0.5, is malignant, and if H theta is less than 0.5, it's a benign tumor. This is not a bad proposal because with this straight line, you can distinguish the two kind of tumors by an algorithm. While the algorithm is set as the output value, if it is more than 0.5, then one kind of tumor, and if it is less than 0.5, then another kind of tumor. But let us suppose there is another test result which is over there with the tumor size of that level. It is also a malignant tumor. So if you want to take all the data and fit through a line of this pattern, then the line may be this one. So if you apply the same logic as we applied earlier, at the 0.5 level, it is either malignant over there, and over there it is benign. But you can easily see due to this point, the classification is not correct because many of the data which is actually malignant, but because of your logic, because of this fitting and applying your logic, you are excluding those file from the those data from the malignant. Rather, you are saying those data is the benign tumor, which is wrong. That means this data is actually all malignant data, and these data all are benign data. You could not classify those. Practically, this should be the boundary. The boundary is such that the boundary tumor size more than this boundary is malignant, and tumor size less than that boundary is benign side. So the hypothesis that we set, that H theta greater than equal to 0.5 predict y equal to 1, and H theta less than 0.5 predict y equal to 0, is not correct if you assume H theta is a linear regression. So this is a problem. That means what should be the hypothesis? You can see the linear hypothesis or the hypothesis like this one is not a good hypothesis for classification problem. One more question arises if you assume the linear regression. As you know, the classification problem, the data output data is only 0 or 1. But if h theta x is a linear equation, it can be more than 1 and it can be less than 0. So what happened to the data which is greater than 0 and less than 0? How will define those data as 0 or 1 for our output? So logistic regression, that means the regression for this classification problem, we want to have a h theta. We are looking for a h theta whose values will be in between 0 and 1. Now let us discuss about logistic regression model. What hypothesis we should use for logistic regression, that is the point of discussion now. In the last slide, we have discussed that we want h theta. That means the hypothesis should be within the range 0 to 1. In the previous examples, in case of linear regression, you have seen the equation for h theta. H theta x is equal to theta transpose of x, where theta and x are two vector, and theta is the parameter vector and x is the feature vector. For linear regression, we use that equation, but for logistic regression, we want to modify the equation a little bit, where h theta x will be function of theta tx. Previously, it was simply theta tx, a linear function. Now it will be a function of that linear expression. So what will be the function? Let us discuss a function which is called sigmoid function, and this function looks like this one. You see the figure. it starting from the zero value, it rises up at zero point 0.5. So the slope increases and then again decreases and it asymptotes to 1. That means at high value of z, it approaches to 1. At low value of z, that means the negative value, the more and more negative value, it approaches towards 0. So this is called sigmoid function. And if we put theta tx instead of z, then we can write g of theta tx equal to 1 over 1 plus e to the power minus theta tx. And this is called sigmoid function or logistic function. And if we use this function as a hypothesis equation, in the hypothesis equation, then it will fit the requirement, which is the value should be between 0 and 1. We have not taken into consideration that how to find out the theta, that means the parameters. In case of logistic regression, we also discuss how to find out theta if h theta is given by g of theta tx, or g of theta tx is nothing but 1 over 1 plus e to the power minus theta tx. Before we discuss about the method of finding theta, let us discuss about the interpretation of hypothesis output. For example, for a certain x, if h of x is determined, what does this number, which is between 0 and 1, means? H of x actually means the estimated probability that y equal to 1 on input x. That means if somebody takes an input of x or applies input of x in our sigmoid function, the output is h of x. The estimated value of h of x is the probability. That means, for example, if x is x0 and x1, where x0 is always 1 and x1 is the tumor size, so this is the only single variable in the classification problem. And if we apply into our sigmoid function, let us say with a given theta, the h of x becomes 0.7. And it means that the probability of the patient to be malignant is 70%. That means the probability of having the patient with a malignant tumor is 70% when the x is certain size. That means the tumor size of a certain value. So for different patient it could be 0.6, a different patient and another patient it could be 0.8. So every time it indicates that the probability of having this patient tumor, malignant tumor, is that percentage. So tell patient that 70% chance of tumor being malignant. So looking into the output value, we can say that the chance of tumor being malignant for this particular patient is 70. So in mathematically, we describe like this. H of x is nothing but probability of y equal to 1, that means probability of having malignant tumor for a certain value of x, which is parameterized by theta. That means with a parameter theta for certain x, the probability will be that value, and the probability for what? Probability for having malignant tumor. And since y can be either 0 and 1, so the probability of the patient to be benign and to be malignant, the summation of the probability must be 1, because either it can be 0 or it can be 1. So if certain patient has a hx value is 0.7, so this value must be 0.3 because the total value has to be 1. That's why we can write this equation in rearranged form. Probability of having benign is nothing but 1 minus probability of having malignant. So our function will give the probability of malignant, and if you want to calculate the probability of benign, you have to subtract that value with a minus 1 minus of probability of having malignant. For example, if a patient has a h of theta value of 0.2, that means his probability of having malignant tumor is 20% only. That means his probability of having benign tumor is 80%. So we can conclude that his tumor is benign, not malignant. Now let us define the logic for logistic regression. That means when we will call a certain prediction as a 1 and when we call it 0. In the previous slide, we have defined the hx as probability of y equal to 1 for certain x parameterized by theta. That means the probability of having y equal to 1 is represented by the hx. The value of hx represents the probability really. And the gz is defined by 1 over 1 plus e to the power minus z, where z is actually theta tx. So this is the function of gz, which is called sigmoid function, and it varies between 0 and 1. And for hx greater than 0.5, the probability is high. When hx is less than 0.5, then probability is low. So what we can define that if gz is more than 0.5, then we can term this is the region of y equal to 1, and if the gz is less than 0.5, that means within this area, then we can call this theta t for those x's, theta t x for those x's is actually 0, y equal to 0. So we may say y equal to 1 if h theta x is greater than equal to 0.5. That means if the value is between 0.5 and 1, the probability 0.5 and 1 for z starting from 0, then we call is y equal to 1. That means we call this as a positive output. In other words, z greater than equal to 0 or theta t x greater than 0. Z is nothing but theta t x. Similarly, y equal to 0, we call it y equal to 0 if theta x is less than 0.5. So this region, if it is less than 0.5 up to 0, or we can say if z is less than 0 or theta t is less than 0, then it is region of y equal to 0. So this region is y equal to 1 and this region is y equal to 0. So in the previous slide, we defined how to determine y equal to 1 and y equal to 0. That means we are now in a position to decide the regions and how to distinguish this boundary. If you want to visualize this decision in features plane, that means in x1 and x2 plane, how this boundary looks like. Let us say this is our data set. Some of the data is benign, the tumor is benign, these data, and these are the malignant data. That means for certain x1 and x2, these are malignant, and for another set of x1, x2, these data are your benign tumors data. So let us say our hsx is theta 0 plus theta 1 x1 plus theta 2 x2, and function of this a function of g, and this is your theta tx. Let us also say that somehow we have determined theta 0, theta 1, theta 2 as minus 3, 1 and 1 respectively. And this portion of the discussion, that means how to determine theta 0, theta 1, theta 2, has not been covered yet. We'll discuss the method of determining thetas. But let us say, following the method, we got the output for this set of data that the theta 0 is minus 3, theta 1 is 1, and theta 2 is 1. That means theta vector is this one, minus 3, 1 and 1, theta 0, theta 1 and theta 2. So as we defined in the earlier slide, that predict y equal to 1 if h theta x is greater than 0.5. So since hx is already defined, so we can say that if theta t is greater than 0, because when hx is greater than 0.5, the z is greater than 0 or theta t x is greater than 0. From the previous slide, you can relate this equation. So theta t is nothing but this expression. So this expression is minus 3 plus 1 multiplied by x1 plus 1 multiplied by x2 is greater than equal to 0. If you rearrange this equation, if we take minus 3 on the other side, then we can say the line representing x1 plus x2 greater than equal to 3, or the region representing x1 plus x2 greater than 3. When this equation satisfied, this is the prediction of y equal to 1. In other words, you can say the prediction will be y equal to 0 if x1 and x2 is less than 3. So this is another boundary or another reason, not boundary, it's another reason where we can say the prediction is 0. So let us draw a line with x1 plus x2 equal to 3. So this will go through this point and this point, 3 and 3. So this region represents where x plus x1 is equal to 3. For example, this is 2 and this is 1. 2 plus 1 is 3. This is 1 and this is 2. So 2 plus 1 is again 3. So this line represents x plus 1 equal to 3. We call it decision boundary because above this line x1 plus x2 is greater than 3, and below this line x1 plus x2 is less than 3. So you can easily see the decision boundary correctly describes the data in the two regions. One is y equal to 1, other is y equal to 0. So the region above this line, these data are y equal to 1, and region below this line, the data is y equal to 0. So if your unknown data is, for example, in this point and in that x2 and x1 is that level, so since this falls with the upper side of the decision boundary, so this will be a malignant case. If your new data is over there, say x1 is that value 0.8 for example, and x2 maybe 1.8, so this value is within the other region, so we can say that this case is a case of benign tumor. Let us show you an example where the decision boundary may be nonlinear. Let us say this is a data set where the circular mark points are the negative examples and the cross marks point at the positive examples. In this case, we'll end up with a decision boundary which is nonlinear. So in order to add nonlinearity in a hypothesis, we have shown in case of multivariable linear regression that you can add the square term or multiplication of the variable terms in the hypothesis by adding like this one, theta 3 x1 square, theta 4 x2 square. So in this hypothesis, we have 5 unknown, which are theta 0, theta 1 up to theta 4, and these are the parameters, and these parameters are obtained from optimization. So let us say we have found out these parameters and the values are minus 1 0, 0, 1, 1. That means the theta vector is like this one, minus 1, 0, 0, 1, 1. So to predict y equal to 1, we will write h theta t should be greater than equal to 0. So if this is your hx, so you just write down all the thetas, and it will be minus 1 plus x1 square plus x2 square, and this will be greater than equal to 0. So by rearranging, we can write x1 square plus x2 square greater than 0. That means the values of x1 and x2 which satisfy this equation at the region for positive example. So x1 square plus x2 square greater than equal to 1. So from that we can write x1 square plus x2 square equal to 1. The line is nothing but a circle, and this circle is the decision boundary for this problem. So you can see the decision boundary in this case is not linear, it's non-linear. Even the decision boundary can be more non-linear. That means non-linearity may not be a regular shape. In that case, the hypothesis function you may choose like this, where x1 square, x1 square, x2, etc. terms exist. So by solving theta 0, theta 1 up to, say, for example, theta 6, you may end up with a nonlinear boundary, decision boundary, which is not of regular shape. It may be something like, say, ellipse, or it may be even a weird shape like this one. And all this decision boundary depends on the given data. In the previous case, the given data was such that it could be separated by a circle. In this case, the decision boundary could be an ellipse, and in that case, the data set may be such that the decision boundary is different. That means a totally nonlinear and irregular shape of decision boundary. Now, the problem at hand is how to determine the parameters theta. We have training set of m examples x1, y1, x2, y2, etc. And each x, that means features, input features, are x0 up to xn. There are n number of features, and the constant feature x0, which is always equal to 1. So in total, n plus 1 number of features. And the output y is either 0 or 1, because this is a case of logistic regression. So it will be either 0 or 1. And hx, that means the hypothesis, is defined by a sigmoid function 1 over 1 plus e to the power minus theta t of x, and the problem is how to choose parameter theta. In order to determine the parameter thetas, the process is you have to determine a cost function. You have to define a cost function, which is normally the square of the error, and you have to determine the lowest cost function for certain theta, and that is the theta we are looking for. So this is the expression of cost function for linear regression. The half term was outside the summation. We have taken half inside for simplicity for the later derivation. And the variation of theta with respect to theta was like this. When theta is a single parameters, and the advantage of convex shape is that whatever may be the initial point, as the iteration proceeds, it always converges to the global minimum point. Let us define the term inside the summation with a new variable called cost. Cost is a function of h, x and y. So where cost hx and y is nothing but the half of hx minus y square. So here the hx is a sigmoid function where the sigmoid function is defined by 1 over 1 plus e to the 1 minus theta t of x. So unlike the previous case, in case of linear, it was a hx was a linear equation, but this time is a nonlinear equation, highly nonlinear equation, and it is 1 over 1 plus e to the power minus theta t x. And because of this nonlinearity, the cost function is, it looks like this one. That means it's a non-convex shape, and there are many local minima, and it is not guaranteed that we can reach to the global minima. So that's why we have to define the cost function in such a way that the variation of cost function is a smooth convex shape so that the convergence is guaranteed. Now we are going to find out a cost function which is applicable for logistic regression, because if we follow the cost function for linear equation or linear regression, the variation is not a convex shape, and this is because of the nonlinear variation of hx. So for linear regression, for the logistic regression, the cost function is defined by this equation. When y equal to 1, the cost is minus log of hx. When y equal to 0, the cost is log of 1 minus hx. And this is logical because when y equal to 1 and if x equal to 1, that means you predicted correctly, so the cost should be 0. But if y equal to 1 and you predicted hx equal to 0, the cost should be infinite, because we have to penalize the learning algorithm by a very large cost. And this is satisfied by this equation, because when you put hx equal to 1, the log of 1 is 0. When you put hx equal to 0, so log of 0 is infinity. So for y equal to 1, the definition of minus log hx as a cost function is very logical. And the variation of this cost function by this mathematical equation is nothing but this one. When hx equal to 1, then it is 0. When hx equal to 0, it is infinity. And in between, it varies with the log. As it approaches the exact output, which is 1 in this case, so the cost reduces. So this equation we should take for cost function for logistic equation, and you see the variation is smooth. There is no up and down of the cost function. Similarly, if y equal to 0, the cost function is defined by this equation. And following the previous discussion, for y equal to 0, if you predicted hx equal to 0, then cost should be 0, because you predicted correctly y is 0 and you predicted also 0. And it is evident from the equation also, if you put hx equal to 0, this is log 1 and log 1 means 0. But if the prediction is wrong, which is 1, and your y value is 0, so you predicted 100% in the opposite direction, so cost is infinity. And if you put hx equal to 1, this becomes 0, so log of 0 is equal to infinity. So in the latter case, we should penalize the learning algorithm by a very large cost. And the variation of cost in this case, when y equal to 0, is this one. When hx is 0, the cost is 0. When hx is 1, the cost is infinite. In this case also, the variation is very smooth. There is no bumping or up and down of the cost function. So in the two region, if we define the two function of cost function, we expect that we will converge to the minimum point. If the output is 0 and you are predicting at a certain point, then you start iteration, it will converge to the your minimum point. Similarly, for the y equal to 1, if you start iterating, then it will converge to the also to the minimum point. So this is the definition of cost function for logistic regression. We discussed about the equation of cost function applicable for logistic regression. There are two equations, one is for y equal to 1, other was for y equal to 0. Now we want to make a simpler equation out of those two equations. The cost function is defined by this equation, where individual costs of individual samples are summed together and make an average. So this was a cost for individual sample for y equal to 1 and for y equal to 0. And note that the y is either 1 or 0. It cannot be 1 and 0 simultaneously. And with this fact, we can combine these two equations. We compress the two equations into a single equation, and the equation will be like this. If you notice carefully, the cost function of individual samples is nothing but minus y multiplied of the equation and minus 1 minus y multiplied by the equation. Since y can be either 1 or 0, for example, if y is 1, this term will exist and this term will vanish. If y equal to 0, this term will exist because 1 minus 0 is 1, and this term, because y is 0, this term will vanish. So in fact, this is nothing but previous to equation, but you can write the equation in a single line or in a single form without having any clause like y equal to 1 and y equal to 0. So this is a combination of the two equations. Say for example y equal to 1, then cost of h theta x and y will be equal to only minus y into log of h theta x, because the second term, which is this term, will be absent because of y is 1, so this becomes 0. Similarly, if y equal to 0, the cost will be equal to only the second term minus 1 minus y of log of 1 minus hx, where the first term will be absent because y is now 0. This is the equation for logistic regression. So what is our objective? Our objective is to fit parameter theta, because we have to have theta for minimum cost. So the algorithm that we've developed, that we have to find out a mechanism to find the minimum j theta and get theta. The final objective is, when we get the theta, we can use the equation of hypothesis to find out the value of the hypothesis or prediction of the output for a certain given x, where output is nothing but actually probability for y having 1. So let us recollect gradient descent algorithm. For logistic regression, we also apply the same algorithm as we applied for linear regression. So this is our equation for logistic regression, and for linear regression the equation is different. So this is j theta, where this each sample cost is summed together and finally we take the average. So if you remember, our objective is to get theta for minimum j theta, and it is the minimization problem over theta. So the convergence equation or the iterative method was like this. We have to update theta until convergence arises. And updating formula, you remember, is nothing but j theta should be replaced by previous j theta minus a learning rate alpha multiplied by derivative of j theta. That means for each j is equal to 0 up to n, that means total n plus 1 number of j. For each j, we have to take derivative of this equation, and then that derivative has to be multiplied by learning rate, and the quantity has to be subtracted from theta j, and we'll get new theta j. Remember that this updating has to be simultaneous updating. Now let us discuss how to determine the derivative of j theta. J theta expression, again, this is the j theta equation, and if we want to take the derivative, we have to differentiate the right hand side. And in the differentiation, there is a term which is the hypothesis, and hypothesis is given by a sigmoid function for logistic regression. Unlike the linear regression, the hypothesis was just theta t multiply x. But in this case, it's another equation which is a nonlinear equation 1 over 1 plus e to the power minus theta t of xi. So if I put that expression in the two places over there, then the equation will look like this one. So you can see, if you want to differentiate with respect to j theta, we have to differentiate the log term. If we differentiate the whole equation, the equation after simplification, it will be like this. And the simplification part we have not shown in this slide because this is not required. Our objective is to find out the final expression. So if you notice the final expression is exactly same as the expression we have derived for linear regression. So algorithm looks very similar to the linear regression because since the derivative term is same, so the iterative algorithm will also be same. Only thing you have to remember, h theta has to be different. H theta for linear regression, just linear equation, and for h theta for logistic regression, it is a sigmoid function. Otherwise, the equation is exactly same. The final form of gradient descent algorithm is like this one. If you replace derivative of j theta with our recently derived derivative of j theta, the expression over there, that expression if you replace in the convergence loop, the equation will now become this one. So this is our final form of gradient descent algorithm. So you have to remember that simultaneous update for all j theta. So this is the equation that we wanted to derive, and the discussion regarding the alpha, the small alpha and large alpha, is also valid for logistic regression. Also, how to monitor whether the convergence is occurring or divergence is occurring. You can follow the same principle that we have applied for linear regression. And the other discussions we covered related to the feature scaling is also applicable for logistic regression. So following the similar procedure, we can proceed for this logistic regression. Only thing you have to remember, the h theta is different. Let us discuss about the optimization algorithm. Apart from gradient descent algorithm, we have other advanced optimization algorithm. And in our course, we'll use one of those instead of gradient descent algorithm. In the gradient descent algorithm, we have to write a code for derivative of j theta. We have an expression, we have derived an expression for derivative of j theta. The expression apparently looks like same for the linear and logistic regression, although the h theta has to be different in the expression. But in any case, we have to write an expression for derivative of j theta, and from that code, we determine derivative for each iteration and use that value in our updating formula. And the optimization algorithm, other than gradient descents, there are algorithms called conjugate gradient. There are algorithms called BFGS. It is named after four mathematicians. And also there is a algorithm called LBFGS, and this is limited memory of the previous algorithm. So in those algorithms, the last three algorithms, in the code function, we have to have code for j theta as well. That means in our code we have expression for j theta, and also we should have expression for derivative of j theta for the latter three cases. And the advantage of those cases are we do not need a manually picking up a alpha. Alpha is picked up by the function automatically. The built-in function available in the octave automatically takes up the alpha because you use an inner loop within the function which is based on the line search algorithm, and this alpha actually modifies over the iteration. So you don't have to bother about the alpha, it takes up alpha on its own. Since it is a very sophisticated and advanced algorithm, it opens faster than the gradient descent. And that is the lucrative feature for us. When the problem is very large, the speed is very important. So that's why instead of gradient descents, we'll prefer to use those advanced algorithms. But theoretically, those are very complex and we don't want to go into the detail of the theory. But as far as use is concerned, our purpose is to use the algorithm, and we'll show you in the next slide how to use this one of those algorithms in our case. Let us now discuss the use of an advanced optimization function in Octave. So let us take an example of a vector having two elements of theta and theta 1 and theta 2. Like in our case, it could be theta 0 and theta 1 for single input. So j theta may be expressed by this equation. Just an example. Theta 1 minus 5 whole square plus theta 2 minus 5 whole square. So you can easily visualize the fact that if theta 1 equal to 5 and theta 2 equal to 5, the j theta becomes 0. So from the optimization algorithm, we expect that the final result will be theta 1 equal to 5 and theta 2 equal to 5. Whatever may be the initial value, after convergence, we expect theta 1 and theta 2 as 5. The expression for derivative of j theta with respect to theta 1 will be twice multiplied by theta 1 minus 5. If you differentiate that equation, that is the result. If you differentiate by with respect to theta 2, then also the expression is 2 multiplied by theta 2 minus 5. So these three expressions you have to codify in a function. And the function name is given here cost function, and the argument for the cost function is theta. Whatever theta you decide that as a input value. So this value you have to put input from the outside, and the output of the function will be j value and gradient. J value is the j theta and gradient is the derivative of j theta. There are two derivative, gradient 1 and gradient 2. So expression has to be written. Also the expression for j theta has to be written. So this is the function that you have to write. And from the command prompt, you have to use these lines to evaluate the or to execute the optimization function, built-in optimization function, which is based on advanced optimization algorithm. So first of all, you have to define a data structure which is optim set. The name of the data structure is optim set. This is also built-in data structure. And in these two data structure, you have to define two parameters. One is called gradient object, and other is maximum number of iteration. And that grad object has to be made on, and you have to put a number for the maximum number of iteration, how many times you want to iterate. So this data structure you have to define first of all, then you have to initialize theta. Let us initialize theta with zeros, and then you have to call the built-in function, which is advanced algorithm for optimization, and this name of the function is fminunc, minimization function, and the parameter for the function is cost function, that is the function that you have already written. So pointer to the cost function is at the rate cost function, and then initial theta, this vector, and also the data structure options. So these three elements you have to put input for the built-in function. So you can easily understand the use of optimization function like this one. So general format of this definition is, you have to first of all define the thetas, where theta 0, if you have theta 0 up to theta n, in octave there is no zero index, you have to always follow the one index. So theta 1 will be the equivalent to theta 0, and theta n plus 1 will be the equivalent to of theta n. And function name is your given name, so you can put any name, and in the argument you have to pass the theta, and so you have to define the function as we defined earlier, and the cost function may be your given name, and theta is your parameter that you want to optimize. And in the function you have to write the code for computing j theta, and also you have to code for gradient, computing gradient with respect to theta 0, with respect to theta 1, up to with respect to theta n. So these are the code you have to write in your function, and in the command prompt, as I defined earlier, you have to put the first of all data structure for options, and then initialization of theta, and calling the optimization function. In Octave, you have to follow it this way, but in case of other language like Python, C++, or R, you have to find out the function for similar optimization algorithm. There are built-in functions in every language, so you have to search for that and use that optimization function for a faster speed. Let us discuss about multi-class classification. In the previous discussion, we discussed about binary classification. That means classification is either 1 or 0, yes or no. But now the classification algorithm would be such that we can differentiate between different groups, like 4 number of groups, 3 number of groups, etc. So not limited to the just 0 or 1, yes or no, etc. Let us discuss some example. Let us say in your email you want to separate out different emails in different groups. Some of the emails are related to work, some of the emails are related to friends, some for families, and some are related to hobbies. So let us assign y equal to 1 for work, y equal to 2 for friends, y equal to 3 for family, and similarly y equal to 4 for hobby. So you can see in this email classification problem there are 4 different possibilities. The another problem in the medical diagram, you can see the person may come with a stuffy nose, and you can actually differentiate between them, like not ill is not actually can be termed as ill. So this is one possibility. Can be cold, it can be cold attacked, it can be a flu. So y equal to 1 for not ill, y equal to 2 for cold, and y equal to 3 for flu. For this problem, there are three classes. Similarly, if you want to classify the weather of a certain day, maybe it's sunny, it's cloudy, it may be rainy, or it is sunny, snowfall. So sunny forecasting, you can make it y equal to 1. If it is a cloudy, then y equal to 2. If the forecast is rainy, so y equal to 3. And for snowfall, you may assign y equal to 4. So what does it mean? It means the classification result, that means the output, is not always limited to 2. There are multiple classes. And the indexing, if you start from 1, it's okay. You can start from 0, it is also okay. So instead of 1, 2, 3, 4, you can assign 0, 1, 2, 3, 4. So now the problem is how to distinguish an unknown into the classes. For example, previously we have two classes, 0 and 1, and an unknown input. If you fit into the algorithm, it will say either it is 0 and 1. How to classify a particular unknown to a certain class, whether it is in the class number 1, whether it is in class number 2 or class number 4, etc. In case of multi-class classification, let us try to formulate how to determine class of an unknown problem. Let us say, in case of binary classification, we mark by different symbols. A cluster of data may be the output. For output equal to 1, we mark by cross, and for output equal to 0, we may mark by circle. Similarly, in case of multi-class classification problem, if there are data set more than 2, then one set of data we may mark by triangle, other set of data we may mark by square, and the third set of data in this diagram may be marked by cross. So there are three classes, so there are three symbols. As we learned earlier, that in case of binary classification, we determine the decision boundary, and this decision boundary gives us the boundary between the two clusters. But in case of multi-class, how to determine these boundaries for different classes? So one to all, one versus all algorithm will tell us how to determine a unknown data, for example, the data over there, whether it belongs to this class or that class or that class. So that is the problem that we are going to solve and discuss in the next slide. Let us now discuss one versus all algorithm. And one versus all algorithm facilitates how to determine the status of a point with respect to multi-class. One versus all classification problem is also called one versus rest classification problem. So let us say we have three set of data. One is marked as a triangle, other is marked as a rectangle or a square, and third one is marked by cross. So class 1, class 2, class 3. So the technique of this algorithm, one versus all algorithm, is that first of all you have to consider one set of data and other two set of data will be treated as a similar data. That means same class of data. So we just convert the three class into two class. For the time being, we just define the green one class kept it intact, and other classes merged together to make it opposite to the previous class. So if green is y equal to 1, then other all data will consider y equal to 0, and we fit our algorithm and we determine the hypothesis. And let us mark h theta 1 of x, the hypothesis. And the line, decision boundary line, could be this one. Similarly, in the second case, we will keep the square shaped data as it is and other two shaped data and take those data as a 0. So this is y equal to 1 and all are y equal to 0. So like the previous one, we can determine another hypothesis which is h theta 2x, and the decision boundary could be this one. In the third case, exactly similarly, we just the crosses as it is, and other two sets of data just considered as a opposite data type. So this is our y equal to 1 and this is our y equal to 0. And this case also will determine the another hypothesis and the decision boundary could be that one. So all these three hypotheses we have to consider for the determination of status of a unknown. So what we will do, we will determine h theta of x for different I from this case, from that case, and from that. Let us say we have one point there, and this point we have to determine for this point whether it belongs to class 1 or class 2 or class 3. And also we will determine the another case, another hypothesis. We consider hypothesis, another hypothesis, and for that exactly that point we will determine the value of hx. Similarly, for the third class, we will also determine the value of h theta x for that point. So it means we will have three values which is expressed by this equation. For y equal to 1, y equal to 2, y equal to 3, what is the value of hx? So in the three cases, we will have three different values, and among these value, whichever is maximum, we will consider that is the class of that particular unknown. Train a logistic regression classifier is theta I x for each class of I to predict the probability that y equal to I. Y could be 1, y could be 2, y could be 3, etc. So on a new input x, to make the prediction, pick the class I that maximizes. We have discussed about linear and logistic regression, and now we'll discuss about a problem in the linear and logistic regression. The problem is called overfitting, and we talk about what is overfitting, and also we'll talk about how to remove this overfitting or how to tackle the problem of overfitting and the technique that is used in machine learning algorithm is called regularization. And we also talk about how to implement regularization in linear and logistic regression. Let us now discuss the problem of overfitting. Let us take the same example of housing price, predicting housing price, and let us say these are the data set. And if you fit by a straight line, that means theta 0 plus theta 1 x, linear regression with single variable, then the curve may be like this one. And this cannot be treated as a good fit because the data shows the price of the house will flatten out when size increases. But your straight line or your regression shows that the line is increasing, the price is increasing as size increasing. We call this underfit. The other name is high bias. High bias is technical name. We'll discuss about the name of high bias later on. The second option may be you use a polynomial. Instead of linear, you just use a hypothesis in the order of x. So in this case, there are three thetas, and if we fit this polynomial using multi-variable linear regression analysis, it may be like this one. So other option is if you assume more nonlinearity like x square, x cube, x4. So in this case, the fitting will be good. You see, the fitted curve passes through all of the example points, but you can easily comment that this fitting or this curve does not represent the normal trend. Normal trend, rather this one, is not a normal trend because it has ups and downs, but price cannot be ups and down as size increases. So we call this overfit, and the other name of this fitting is called high variance. And this is again a technical name. We discussed about bias and variance in later part of our lecture, probably in other lecture. And the middle one is almost right. That's why we just call just right. So this is the case of overfitting. So what is overfitting? Overfitting is if you have too many features, the learned hypothesis may fit training set very well, but it fails to generalize new examples. That means predict price on new examples. The training set fitting is very well. It means that the error is almost zero. That means cost function value is almost zero because the prediction at every point and the actual result are almost same. So the error is almost zero. That's why overall cost function is also almost zero. Although it fitted the all given points, we cannot say this is a good fit because the fitting should be a smooth. It cannot be up and down. That's why if you want to find out this price for a certain size, for example, of that size, it will show the price over there, but it cannot be price over there because the previous and the point after shows that it should be almost a straight line over the 3 points. So it fails to generalize new example. That is the important point. The term generalize. That means all other point other than these given examples, we have to predict with confidence. But in this case, you see the ups and down causes that the actual value or the predicted value is not the real representation of the given data. Overfitting in case of logistic regression. Similar to the linear regression, in case of logistic regression, there may be case of overfitting. Say for example, you have two features x1 and x2 and you want to distinguish between that true and false or positive and negative. And you see on the curve the red points are the positive cases and the circular points are the negative cases. So if you want to draw the decision boundary for different hypotheses, for example, hypothesis like this linear case where g is the sigmoid function, and if we fit the sigmoid function to determine the hypothesis through this point, the decision boundary will be like this. And you can see this cannot be treated as a good fit because the decision is not correct in many of the cases. That's why you call it underfit, and also it is a high bias case. If you include the quadratic term, for example, theta cube x1 square, theta 4 x2 square, theta 5 x1 and x2, so this term if you add with the linear term, then the sigmoid function will be different and the decision boundary will be nonlinear, like this one, for example. And this is not bad, but if you include more power of x, that means high order x's, then you can end up with a very good fit if you see. each and every positive is excluded from the negative, and we can say the fitting is very good, but you cannot treat this as a very good decision boundary because it is not generalized. Any unknown point, it may not be able to distinguish. For the known point, it is okay, but for unknown point, it may be this non-uniform shape may create a problem in distinguish the positive or negative result. So we call it overfit or high variance. So overfitting problem is common for linear and logistic regression. So we'll address this problem and how to overcome this problem. We'll discuss in the next slides. Now let us discuss how to address this problem of overfitting. In case of housing price problem, the number of variables in case of linear regression, we discussed there is one. So the shape of the fitted curve we can easily visualize. In case of logistic regression, we have discussed about two features, and because of two features you can draw the decision boundary. But if the number of features is very high, it is very difficult to draw this kind of figures like fitted curve or decision boundary, and it is very difficult to visualize the problem that is happening due to overfitting. For example, in case of housing problem, if the number of features, for example, 100, and you are totally lost what to do with the overfitting because you cannot visualize the problem of overfitting by drawing on a card. So there are two ways or two options to tackle with this problem. First option is reduce the number of features. So you can manually select which features to keep. You can judge the importance of the feature and accordingly you discard some of them and keep the important ones. The other technique is there is a model selection algorithm which we'll discuss later on in the course, and this algorithm decides which features to keep and which features to remove. But the problem is this algorithm may not give you the correct decision in some cases. The other option is called regularization. That is the topics that we want to discuss. The idea is to keep all the features but reduce magnitude and values of parameter theta j, and that will be automatically. Through the mathematical formulation, you can keep all the features with less or more importance. The degree of importance you can vary. It works well when we have a lot of features, each of which contributes a bit to predicting y. You are not removing anything, so all features have been considered, but some features will contribute more in deciding the price, and some feature may contribute less. So, what is the intuition behind the regularization? Let us discuss about the pricing problem that we elaborated in the previous slide. If you want to fit the data points through a quadratic equation, then the curve may be like this. If you add high order polynomial, the fitting is good because it goes through all the points, but it is not a generalized fitting because the unknown points does not match with the given points. So suppose you penalize and make theta 3, theta 4 really small. These terms, if they could be made really small, then the equation influenced by the first three terms. So if you remember, the objective function of optimization was minimize with respect to theta this expression where hxi consisting of all the thetas. In case of linear regression, this is a linear equation. In case of logistic regression, that is a sigmoid function. And with this objective function, if we add two terms like 1000 theta square, theta 3 square, and 1000 theta 4 square, and then we minimize because we wanted to make the cost as minimum as possible. So if these terms has to be minimized, then theta 3 has to be very, very small. And theta 3 and theta 4 at the minimum cost function, it will be very close to 0. In other words, these terms will vanish. It will not vanish altogether, but it will have a tiny contribution. It indicates that if higher terms has a tiny contribution, then the other term will influence the fitted curve. So instead of irregular shape, it will be close to the regular shape. It may not be exactly the previous one because the other two terms has got tiny contribution, but it will be better than the curve that we have shown here. In the previous slide, we have seen that some of the parameters, if you can make it small, the simulation or the fitted curve becomes very close to the good fit. That means just right curve we can achieve by minimizing parameters of having influence on the overfitting. So now let us propose instead of having certain parameters, targeting certain parameters to be small, let us target all the parameters for making them small. Why all the parameters? Because in the previous example we knew that theta 3 and theta 4 is the problematic parameter. But the problems in different parameters may be influential, and there are some parameters which may not be influential for overfitting. So if I attempt to make all the parameters small, only those parameters will be small through the algorithm or through the process. Only those are influential for the overfitting. In the previous case, we minimizes theta 3 and theta 4, but in general, we should try to minimize all of them, and some of them will be close to the zero, someone will not be close to the zero through the algorithm. And since we are making all the parameters trying to make them small, so it is a simple hypothesis and it will less prone to overfitting. In housing problem, the number of features may be, for example, 100 and the parameters theta 0 up to theta n. So if we keep all the features, then we have to make the formula of cost function where we wanted to minimize all of them. So the cost function for linear and logistic regression algorithm is this one. If you want to consider the regularization, then you have to add the term like this, lambda multiplied by theta j square, summation of theta j square, where j varies from 1 to n. Conventionally, you have to apply the regularization from j equal to 1 to n. You have to exclude theta 0. So theta 1, theta 2 up to theta n, but theta 0 is excluded. You don't minimize the theta 0. Theta 0 is a constant term, the intercept term related to theta 0. And the regularization you have to apply from j equal to 1 to n. When you minimize this function, the theta will be determined, and you remember how to determine theta. You just do the iterative process, and through the iterative process you apply the gradient descent algorithm, for example, and determine the theta. And through the process, only those theta will be close to zero which are influential to the overfitting. Now we have stated the equation for cost function including regularization. The equation is this one, where the first part is our the previous equation for cost function, expression for cost function, and the next part we have just added to consider the regularization. And these two part has two different objectives. The first part is minimizing the error. You see the error, the square has been taken and summation is made. So the total error of prediction is being considered, and we wanted to minimize this cost function means we want to minimize the error between the prediction and the actual output. And the second part, we want to make the theta small. So this objective, if we can fulfill, then the overfitting problem will be removed. And what lambda does? Lambda first of all is called regularization parameter, and lambda actually doing the trade-off between the two objectives. So with the certain value of lambda, the thetas will be set in a such a way that it will not overfit the curve, but the error will be minimized. And in case of pricing problem, house pricing problem, the regularization term, if we exclude the regularization term, then we end up with this kind of curvy shape of fitted curve. But if we add this term while we are doing the minimization problem, then the curve may be like this one. So how it happens? The mathematical background we have not elaborated. When we apply in certain example, the idea will be clearer. And with this process, the only the thetas will be close to zero, which are influential for the overfitting. We discussed about cost function for regularized linear regression and also regularized logistic regression. Let us now discuss how the gradient descent will be modified in case of those two regression analysis. So if you want to include the regularization in case of linear or logistic regression in the gradient descent algorithm, so let us recollect our memory about the algorithm that we have followed for gradient descent. You see the formula that we have developed for gradient descent. The theta j, that means all theta, has to be replaced by the previous theta minus alpha. Alpha is the learning rate multiplied by the derivative of j theta with respect to theta. And this expression is identical both for linear and logistic regression. Let us divide this equation into two. One is only for theta equal to 0, other is other is for all other thetas, where j varies from 1 to n. So 0 has been taken separately because we will not apply, and we do not apply the regularization term with theta 0. The regularization term is only applied for j equal to 1 to n. So this is the now our equation, and we want to see how to add the regularization term with the latter equation. So this is our cost function. The first term is the as usual cost function, and the last term is the regularization term, where lambda is the regularization parameter and summation of theta j square is the summation of all the theta j squares. So there are two terms, and previously we differentiated that term and we end up with these equations, and we have to add a differential term for this equation. And if you differentiate this term with a certain theta j, So it will be twice theta j, lambda of twice theta j. So with the previous equation, we will add just a term 2 lambda theta j. So this is our new equation, and the new equation is just 2 lambda j theta j. That's why the equation, if you simplify this equation, the equation will be like this. If you take theta j term, there are two terms, theta j and this also theta j. If you take the theta j term altogether and keep other terms separately, the theta j equation will be like this. So the second equation has to be replaced by this equation. We also discussed another topics which is called normal equation. Normal equation is unlike our iterative equation or iterative method. So in the normal equation, you can get the thetas directly by solving equation without going into the iterative process. You can put the values of all matrices and you can find out the theta matrix. And in the development, we have shown you that first of all, you have to find out the design matrix. Capital X is called design matrix. If you remember, and if you could follow the lecture 3. In the lecture 3, we have shown how to form this one. X1 is the first example input vector, and you have to transport this vector, transpose of all the input vectors, you have to arrange in X, and the output quantities you have to set in another vector called Y. Once you get capital X and small y, you have to solve equation called theta equal to x transpose multiplied by x and whole multiplied and inverse, and then again multiplied by x transpose and also y. So that will give you theta vector, and this you can get directly by solving this equation. When you want to add the regularization term, the equation is the previous one, but you have to insert one term is inside this inverse equation, and the term is this one. A matrix, diagonal matrix, with first term is 0 and second diagonal elements up to the last diagonal element, all are 1, and all of diagonal elements will be zeros, and that particular matrix has to be multiplied by lambda, which is your regularization term, and then you have to follow the equation that written here. So this is the only modification that you have to make so that you get a modified theta for regularization. Now let us discuss the inclusion of regularization term in logistic regression. Let us take this example where the positive cases are marked by red crosses and the zero cases or the false cases is marked by circles. So truth and false, the two types of data. If you want to draw a decision boundary for certain hypothesis, for example, the hypothesis contains very high order polynomials, then the fitting of the decision boundary may be very good. That means it separates out all the crosses from the circles. So although the decision boundary is very good, but it is not generalized. If you want to determine the status of unknown point, it may not predict correctly. That's why we have to include the regularization term in the cost function. And this cost function is for logistic regression. And if you want to include the regularization term as before, and that will be the term that we have to add, the regularization parameter and summation of all the theta. So by including this regularization term, you may end up with a decision boundary which is more or less uniform. So this nonlinear regularized decision boundary will give you better simulation. That means better decision boundary because it is a generalized one. The term generalized is used for the capability of the algorithm to distinguish between 0 and 1 for the unknown cases. Now let us discuss how to update theta considering regularization for logistic regression. This iterative algorithm, you see the j varies from 0 to 1, and then we divided this expression into two terms, two equations. One is for only j equal to 0, other is for only j equal to 1 to n. So first term where j is equal to 0, that means for theta 0, there is no regularization term. In other cases, there is a regularization term. Since this equation, which is rate of change of cost function with respect to theta, remains same for the logistic and linear regression. That's why the derivation that we have shown earlier is same. So following the discussion of slide number 33, this is slide number 36, we have discussed these two equations. One is for theta 0 and other is for theta z. Only difference in the two regression is that the h theta is different. In case of linear regression, h theta xi is just theta t multiplied by x, and in case of logistic regression, that is our point of discussion now, is this equation, sigmoid function, 1 plus e to the power minus theta t multiplied by x. So the equation is same, but the hx expression for hx that we have to consider in the iterative process has to be taken separately because this is for logistic regression. Now let us discuss how to include the regularization term in advanced optimization algorithm. In the advanced optimization algorithm, we used a built-in function. We have not discussed about the detail of the advanced algorithm. We just showed you how to use the built-in function that is available in Octave. Also, similar function is available in other languages also. But for using that advanced function, we have to write a user-defined function. The function structure was given in the previous slide, and name of the function, since it is user-defined function, is dependent on the user. You can change this name of the function, and then the body you have to write the different line. One is for code for j theta, other is for different gradient. And if you remember, the theta index starts from 0, that is 0 index theta in mathematical expression, but in computer or in Octave, the index has to start from 1. That's why it will, first one is theta 1, the last one is theta n plus 1. So first line of the code, you have to write the expression for j theta. That means code for this right hand side expression. In the expression, you notice that the last term is the regularization term. Lambda is the regularization parameter. And then you have to write the different codes for different derivative. For example, this is the expression for derivative of j with respect to theta 0. There is no regularization term with the expression. But for other expression, there is a regularization term starting from delta by m theta 1 up to delta m by theta n. So these are the lines that you have to write. Of course, from 2 to n plus 1, the expression are similar. That's why you can put a loop where the index can be varied from 2 to n plus 1, where the expression can be generalized. So this is how you can actually use the optimization function. Instead of writing your own function following the gradient descent algorithm, you can use this function to evaluate the derivative or to evaluate the new theta. So the lines that you have to write in the command prompt or maybe in the program also. The first of all, you have to define the option. Optiset is the built-in function, and with the optiset, you have to give two parameters. One is grad obj, and other is max iter. And grab dog has to be on. The data of grab dog is on, and max iter is the maximum iteration. The number has to be given. How much iteration it will try, how many iteration it will try, and then initial theta you initialize with 0, and then you call the function f min u and c. That is the name of the function, and within the function the parameters are cost function pointed to the cost function. This function, the body of this function, that will be taken in the first parameter, and initial theta, the theta that you have defined, and the options mean this data structure. So this way you can just find out the optimum theta. Optimum theta means the final solution of the theta. The process that you will follow has not been discussed, and we don't want to go into the detail of the theory. Just you have to know how to use this function. So let me summarize these topics. What you have to do, you have to write a function where the code for j theta and derivatives has to be written. That's all. And in the command prompt or in a program, you have to write 3 lines. One is a data structure, other is initialization of theta, and third one is the execution of the built-in optimization function. That will give you the optimum theta. With this, we conclude this lecture, and these lectures actually covers two topics. One is logistic regression, detail of the logistic regression, how to implement logistic regression, and also give a glimpse of using the multi-state logistic regression, and then finally we discussed about the regularization. So that's all. Thank you very much.